Hi everyone, today we're going to be covering 6.8, Enthalpy of Formation. So we've already talked a little bit about enthalpy of formation in the context of calculating an enthalpy of a reaction, but I just wanted to spend some time giving actual definitions here and outlining a few things. And so an enthalpy of formation, or delta HF, is defined as the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental form. In other words, it's basically the enthalpy that is required to make any sort of compound from its elements. That's all that this is saying. The same rules apply as before. Bond breaking is endothermic. In other words, it requires energy to break a bond. So delta H is positive because you're going to give energy to the system to break the bond. And bond forming is exothermic. Delta H is negative because once you make that new compound, it releases some sort of energy into its environment. Now, there are also what are known as standard enthalpies of formation. So the standard enthalpy of formation, we denote this as delta HF with this little 0 at the top, and it means that it is measured under standard conditions. Those standard conditions being 1 mole, 25 degrees Celsius, or 298 Kelvin, and 1.00 atmosphere of pressure. The delta H of formation, the standard enthalpy of formation, or delta HF0, is defined under these conditions. And this can be used to calculate the enthalpy of a reaction, delta H0 of a reaction, or essentially the enthalpy of an entire reaction, assuming 1 mole of product made, it's at 25 degrees Celsius, and 1 atmosphere of pressure. One important thing to note is that the standard enthalpies of formation, again, this is delta H F naught, of elements in their standard states, so elements in their standard states do not have an enthalpy of formation. Otherwise, in other words, for something like O2, its delta H F naught is equal to 0 kilojoules per mole. And so the list you need to remember is that for any diatomic, so those are O2, N2, F2, Cl2, Br2, and I2, and then any other elements. So, for example, like iron solid or carbon, for example, or we'll take one more, Zr or zirconium. Right, for all of these, it's equal to 0 kilojoules per mole. So anytime you see an element in its standard state, it's 0 kilojoules per mole. We've already had a little bit of practice with this previously, but if you're trying to find the enthalpy of a reaction under standard conditions, or again, 298 Kelvin, 1 atmosphere, and 1 mole of your reaction, or of your products, then it's just the sum of delta H of your products minus the sum of delta H of your reactants. And you've got to remember that when you're doing this, you always want to put some brackets around here to kind of help you out. Here's just a table of standard enthalpies of formation. You don't need to memorize this, and it's not a completely exhaustive list, but it's just some examples of enthalpies of formation that you might see for some standard compounds. And so I just want to do one practice problem on this video before ending it off. In this practice problem, we're told that we have a reaction of aluminum reacting with iron oxide to form solid iron and aluminum oxide. Of course, aluminum and iron, both of those are in their elemental form, and so it's equal to 0. So I'll write here, these are elemental. Their enthalpies of formation are going to be 0 because it's the way that you expect to find it in its most standard state. Right up here, we're given, actually, delta H of the reaction. That's equal to negative 860 kilojoules per mole. And so we're not finding the delta H of the reaction, and instead, what we're looking for is delta H of iron oxide. Again, we got to think about how to set up this reaction. I'll do it down here. Delta H naught of the reaction equals the sum of products minus reactants. So for products, this is going to be 2 times the delta H of iron, and then that's going to be plus 1 times the delta H of formation of aluminum oxide. We're going to subtract all of that by our reactants, which is 2 times delta H F naught of aluminum. And then that is going to be plus 1 times the delta H F naught of iron oxide. And of course, this is what we're interested in. So if we go ahead and plug in numbers here, negative 860 kilojoules per mole is equal to 2 times 0, right, because iron is 0, plus the delta H of aluminum oxide, which is negative 1,680 kilojoules per mole. We're going to subtract this by 2 times aluminum, which again is 0, plus 1 times Fe2O3, which is what we're interested in finding. I'm not going to go through all of the arithmetic to do this, but the delta H F naught of iron oxide is negative 820 kilojoules per mole. That's all that I have for this video. Otherwise, thanks, guys.